Okay, so as you all know, this is a series of 3 lectures. In this first lecture, I'm going to be describing the problems that the determinant method addresses, because you won't understand the point of the thing unless you realize what it is we're trying to do with it. And I'll end up by describing some of the results that the determinant method can prove. So there'll be very little by way of proof in this lecture. Tomorrow, we're going to look at the basic result of the p-adic determinant method. We'll give more or less full proofs for that. And in the third lecture, we'll look at some other forms of the determinant method. And in particular, we'll look at the approximate determinant method. So that's the program. There are a couple of references that you might find useful. I'm hoping that you'll be able to access my slides in due course, so don't necessarily try and write these down now. The first of these, though, Annals of Math from 2002, this is a paper on the basics of the determinant method, p-adic determinant method, where the key theorems were established. The second reference, some lecture notes on a series of lectures somewhat like these, but this series will be an updated version. Okay, so here's the basic problem in various...
Roger, I'm sorry to interrupt. I think we're not seeing your slides advance.
Ah. Okay.
In fact, they looked bigger before you moved to full screen mode. I know that's an irony.
Let me try and go back and see if we can do that. Okay, so can we now see slide 2?
Yes.
Good. So here are the references. Here is slide 3. Yes?
Yes.
Excellent. Okay.
Thank you.
So in the simplest version, one has a polynomial f in several variables with integer coefficients. And one has a counting function nb, which depends on the polynomial f. It's the number of integer vectors x, so bold x will be an integer vector, which are solutions of fx equals 0 in what I think of as a box, norm x less than or equal to b. Now one can take various norms here. It makes very little difference to the results which sort of norm one takes. I usually work with the sup. And then the key question is, how does this counting function grow when the size of the box tends to infinity? So fx equals 0 will be a Diophantine equation. We're looking at an integer equation with integer variables, and we're looking at the sorts of Diophantine equations where we expect there to be infinitely many solutions. One can also ask about systems of Diophantine equations. There'll be an analogous counting function. Alternatively, one can think in terms of an algebraic variety V in affine space, defined over the integers, and look at the affine counting function for that variety, which will be the number of integer points on V with height at most B, where the height of the point is defined in terms of this norm constraint. Alternatively, one might look at a projective variety. So one would have a system of homogeneous equations in n variables, so this is in n-1 space. And then the projective count will be the number of rational points with height at most b. And for a rational point, you would, or the naive method of measuring the height would be to clear any common denominators from this rational vector, remove any common factors, and then look at the subnorm of the resulting integer vector. So in all these cases, we're thinking probably in terms of Diophantine equations or varieties that have infinitely many points, and one wants to know something about the growth rate of the associated counting function. Well, why should we care about these questions? Well, you could argue that these questions are interesting in their own right. It's rather like doing geometry over Q, and you're trying to relate it to the properties of the underlying variety. So you're relating the geometry over Q to the geometry over Q bar. And the properties of the counting function turn out to be related to the geometry of the variety in question. You could be interested in much more arithmetical questions. So if you look at this particular Diophantine equation where you have m integers on the left and you add up their case powers, and another m integers on the right and you add up their case powers, if you get equal sums, well, if you could prove the conjectured upper bound for this equation, so there is a conjecture as to how large NB should grow in this instance, if you could prove that, you get a very good result for Waring's problem. This would say that every sufficiently large integer is a sum of 4k non-negative case powers. This is distinctly better than we can prove at the moment. Indeed, you could prove the classical Hardy-Little asymptotic formula for the number of representations as soon as there are at least 2k plus 1 variables. So questions about the growth rate of NB could be applied to Waring's problem. Here's another rather different example. If you took the equation x squared plus dy squared equals z to the k and counted solutions in which z is at most d to the 1/2, well, again, there's a conjecture as to how many solutions you might have. And if you could prove the conjectured upper bound, we could deduce something about the class group for the field, number field Q adjoins square root minus d. That's to say that the K part of the class group has size at most d to the epsilon for any small positive epsilon, no matter how small. This notation, I remind you, means that there is an inequality involving a hidden constant which depends on epsilon on k, but not on d. So one can prove something about class groups of quadratic fields. Here's another arithmetic question. If you take an irreducible polynomial f and consider the equation f of x equals yz squared with size constraints on the integers y and z, again, if you could prove the conjectured upper bound, we'd be able to establish the old conjecture that f takes infinitely many square free values if there's no local obstruction. So we believe that the polynomial x to the 10 plus 1, for example, takes infinitely many square free values, but that's never been proved. And a suitable result on the counting function for this equation would allow one to establish that. Well, what do we expect about the counting function NB? Well, there's a very naive heuristic argument that gives some rule of thumb as to what to expect. Let's imagine that we have a homogeneous polynomial of degree d. And we look at the integer vectors in this box, norm x less than or equal to b. Well, there are something like 2b to the power n such integer vectors. Each coordinate of x runs from -b to +b. Now, because f has degree d, the size of the values of f of x will be at most some constant times b to the d. The constant here will depend on the coefficients of the form f. Now imagine that you have a row of boxes labeled from -b to the d to +b to the d, and you have something like 2b to the n balls, and you throw them at these boxes at random. How many of these balls are going to land in the box labeled 0? Well, you have this many boxes. The probability of getting your ball into the box labeled 0 is b to the -d. So you might expect b to the n minus d hits. So this argument suggests that the equation fx equals 0 might have something like b to the n minus d solutions when x is a vector of this size. Well, there are many, many reasons why this can go wrong. For example, this would be ridiculous if n, the number of variables, was less than d. You'd have an exponent here that was negative. Anyway, as a first try, we have this suggestion that when the number of variables is bigger than the degree, then the counting function should grow like b to the n minus d. Bigger than a certain constant times b to the n minus d, less than some other constant times b to the n minus d. With this proviso, unless there is a reason why not. Well, to back that up, there is a famous theorem due to Birch, dating from 1961. And it says that if capital F is a non-singular form of degree d, and the number of variables is pretty large, more than 2 to the d times d minus 1, then there is a constant, positive constant, depending on the form f, such that the growth rate nbf is asymptotically constant times b to the n minus d. And that's assuming that there are solutions of this equation, non-trivial solutions in R and in each p-adic field, QP. After all, if f was a quadratic form, negative definite, then the only solution fx equals 0 would be the 0 vector. You want to rule out situations like that, so you need to assume there's a non-trivial solution over R, and similarly over the p-adic fields. But in these situations, you genuinely do get a growth rate of size b to the n minus d. So that's good news. In fact, there's an extension of this to general varieties in projective space. So if V is smooth, absolutely irreducible, of degree d, a similar constraint on the dimension, then again, the projective count of points on V will be constant times b to the k plus 2 minus d, providing V has points over R and each p-adic field. Now, you might be surprised that the condition here is different from the one we had before, and the exponent there is different from what we had before, but that's merely because you have to add and subtract 1 when you go from projective dimensions to number of variables. So in fact, the condition here translates exactly to the Birch condition. The exponent there translates exactly to the Birch exponent. So the key things here are firstly that the variety must be smooth, and secondly that the dimension has to be pretty high for these theorems to work. Okay, well, let's think about the things that could go wrong with this prediction that b to the n of b should grow like b to the n minus d. Well, we've already mentioned the possibility that the number of variables n should be less than the degree, in which case b to the n minus d will tend to 0. So that's obviously something one needs to worry about. Things can also go wrong when n is equal to d. So there are various things that can go wrong in this case. One is that if you take f to be homogeneous, then as soon as there's one non-trivial solution of an integer value x naught other than 0, well, then it will have something like order b scalar multiples in this box. And each of these scalar multiples will also be a solution of fx equals 0 because of the homogeneous property. So automatically, n of bf will be at least of order b. Well, this doesn't require n to be equal to d. This is true in general. And this is the reason that we tend to use the projective formulation whenever we have homogeneous equations. Here's an example with n equals d equals 3. It's the equation for an elliptic curve in projective 2 space. Now, in this case, if we count the number of projective points at height at most b, this will grow like a constant times a power of log b to the r over 2, where r is the rank of the curve. So this is a bit unexpected. We were expecting a power of b to the n minus d. Well, we do have the correct power of b because in this instance, n minus d is 3 minus 3, it's 0. So we do have b to the 0, but we have some extra logarithms in general. There's nothing in our heuristic argument that would have predicted that. Here's another example where we take the variety given by this quadratic equation in 4 variables. So this is a quadric surface in P2. Now, it's not difficult to show, I'm not going to do it here, but that the projective count grows like b squared log b with an extra logarithm. So here we have n equals 4 variables and d equals 2, degree 2. So b to the n minus d would be b squared. That much is correct, but we have this extra logarithm. Well, there's a soft way of getting around those difficulties. So let's revise the heuristic expectation. Suppose that f is now homogeneous, and let's have a projective variety v in n-1 space. That corresponds to f having n variables. So this is a hypersurface given by f equals 0. Then, providing n is at least d, we're expecting the projective count to grow at least like b to the n minus d, and at most like b to the n minus d plus epsilon. So here again, epsilon can be an arbitrarily small positive constant, but the implied constant here is allowed to depend on what epsilon is. And again, with the silly proviso, unless we can think of a reason why it shouldn't be true anyway. Right. So that's what we hope to be true. But things can still go wrong. Here's yet another example. So here we're going to take a 4-variable equation, degree 3. So this is defining a cubic projective surface. So n here is 4. The degree d is 3. So n minus d equals 1. So we would have expected something like b to the first power for the number of solutions. But we can easily see solutions of the type A minus A, B minus B. All those points are automatically solutions of this equation. And since we're allowing solutions of size at most capital B, A can run up to capital B, little b can run up to capital B, so there'll be something like B squared solutions. Too many solutions for this trivial reason. So we'll make yet another modification to our heuristic expectation. We'll exclude trivial solutions. That's fine, but we need to work out what trivial means. Well, what's happening here is that these points make up a line in projective space. And it's a line that is contained in this variety. Well, that's just another way of saying that all these points satisfy this equation. So generally, if we have a surface in projective space, we'll take capital U to be the complement in the surface of all those lines that are contained in the surface. So we just rule out points that lie on lines. And then we'll define a modified counting function with a subscript 1 here to be the number of points that lie on this set U, this open set. Again with, sorry, that should be a math bold Q, rational points on this surface U of height at most B. Now, it's quite possible for a surface to be made up exclusively of lines, so that all points lie on a line. We have a ruled surface. And in that case, this set U will be empty, and it's quite easy to estimate the size of the growth function. But in general, there'll only be a finite number of lines. Points on the lines will make up a contribution order B squared, and it's the remaining ones that are interesting for us. So that takes us to Manin's conjecture in the case of smooth cubic surfaces. So in the case of a smooth cubic surface in projective 3 space, providing there's at least one rational point, the conjecture will say that the growth function here, this is a counting function that excludes points on lines. Then this should grow like constant times b times the suitable power of log b. And the power conjectured by Manin is rho minus 1, where rho is an integer between 1 and 7, and it's the rank of the Picard group of V. So here we have b to the first power, that's n minus d in this case. N is 4 variables, degree 3, but with some extra logarithms. Sadly, in the case of smooth cubic surfaces, we don't know of a single instance where this has yet to be proved, has yet been proved. But it's one of the main motivating questions in the study of surfaces.
Roger, we have a question in the chat asking about whether there are any cases known where something bigger than a logarithm is the extra factor.
Good question. The answer is no. Sometimes you will have to rule out more than lines, but if you choose a suitable open set, it's believed that most extra logarithms will be required for projective surface, for projective varieties. Weird things happen with affine varieties. Okay. So, what methods do we have available to estimate the counting function? Well, I've already mentioned the theorem of Birch, which was proved by the Hardy-Littlewood circle method. So we're not going to look at the circle method, but its key features are these. First of all, it's a global method. The information input is an understanding of how the polynomial f depends modulo q for all moduli q. If there's even one modulus where we don't understand how f behaves, then we can't make the circle method work. Secondly, it works best when n is relatively large compared to d. And we saw in Birch's theorem that n has to be exponentially large in terms of d for that particular theorem. It requires some sort of smoothness properties. And the version of Birch's theorem that I quoted actually requires the variety to be smooth. In fact, all that Birch requires is that it has a certain degree of smoothness. And it is most effective when there is some sort of additive structure. So in particular, if you have diagonal or Fermat varieties, where the polynomial f is made up of a sum of terms cj times xj to the d, then it will work very well then. It works in other situations, but that's when you get the best results. One can also use sieve methods. These were initiated by Hooley. The square sieve is the best known version of this. This again is a global method in the weaker sense that one needs to understand f modulo q for many, but not necessarily all moduli q. Whereas the circle method is capable of giving an asymptotic formula, the square sieve and sieve methods in general will only give you an upper bound for the counting function nb. Things work most easily when there is a variable which appears in only one of the terms. So again, there is some sort of structural requirement for the polynomial f. And the method draws its strength from bounds for exponential sums of Deligne type. So complete exponential sums to a prime modulus, we will often have a square root saving, which is very effective in this context. One very simple method is just to use congruences. So the counting function nb will clearly be at most the number of solutions, integer solutions of fx congruent to 0 modulo q inside a box of size b. So this is clearly a local method. One needs to understand f modulo q for a single well-chosen modulus q. And again, this takes advantage of bounds of for exponential sums of Deligne type. It seems surprising that in some circumstances, just using a congruence like this will give us the best result currently available, but that is indeed the case. And finally, there is the Bombieri-Pila method dating from 1989, and this is where the determinant method has its birth. So one theorem proved by Bombieri and Pila is the following, that if you have an absolutely irreducible polynomial in two variables of degree d, then the counting function grows like at most as fast as b to the 1 over d plus epsilon for any fixed positive epsilon. And I need to emphasize that the implied constant here will depend on epsilon and d, but is otherwise independent of f. So let's look at the example x to the d minus y. This is an absolutely irreducible polynomial of degree d. And we can see solutions of f equals 0 of the type x equals a, y equals a to the d. And we want to count solutions of size at most b. So in particular, a to the d has to be at most b. So a can run up from 1 up to b to the 1 over d. And that will provide b to the 1 over d solutions. So for this polynomial, there are at least b to the 1 over d solutions. Here they are. So this exponent 1 over d is going to be best possible. And so the result is best possible apart from the epsilon there. So the proof here is by a local method. And in the Bombieri-Pila case, it's using properties over R. And in effect, one is counting points where f of x, y is very small without actually needing f to be equal to 0. And I should emphasize, and it's important for other applications of this method, that their result can be modified to handle suitable functions which are not polynomials, they're just C infinity functions. So that takes us on to the determinant method. So these are results produced by the p-adic version of the determinant method. So this method handles polynomials in any number of variables, not just 2, as in the Bombieri-Pila case. It has both affine and projective versions and a biprojective version, etc. Again, it's a local method, depending only on properties of f modulo powers of p. And in effect, it's counting points where fx is p-adically small, rather than actually needing f to be equal to 0. And just as in the Bombieri-Pila case, it provides upper bounds with a constant that, well, in this case, depends on the number of variables n, as well as d and epsilon, but is otherwise independent of f. So here are some of the basic theorems proved by the p-adic determinant method. First of all, it will give another proof of the Bombieri-Pila theorem for polynomials in 2 variables. So whereas this theorem was proved by real analytic methods, you get exactly the same theorem by p-adic methods. Let's consider the case of a form in 3 variables that corresponds to a curve in P2 with f absolutely irreducible of degree d. But in this case, the projective count, counting projective points, is at most b to the 2 over d plus epsilon. So in the Bombieri-Pila theorem, we had 1 over d plus epsilon. So that was for an affine curve. For a projective curve, where we're counting rational points rather than just integer points, we get exponent 2 over d plus epsilon. For surfaces in P3, given by a form in 4 variables, absolutely irreducible of degree d, then the count of projective points is of order at most b to the 2 plus epsilon. So we'll look later at, I'm just understanding what the quality of these exponents here is. So this is counting all projective points, but now if we have the subscript 1, so we're excluding trivial points, points on lines contained in the surface, then we get an exponent that is strictly less than 2. So in the paper that I cited right at the beginning, we see an exponent 52/27, strictly less than 2. So in the second statement, that's the one here where you have a curve in P2 given by a form in 3 variables with exponent 2/d. That exponent is best possible. So here's an example where the form is x1, x2 to the d minus 1 less x3 to the d. And you can see that there are solutions of the type a to the d, b to the d, and a times b to the d minus 1. All those points make f equal to 0. And if you take a and b to be of size at most capital B to the 1/d, that will provide b to the 2/d pairs, and requiring, you would want a and b to be co-prime to make sure that the rational points you're getting are all distinct, but that reduces the number of points only by a constant factor. So you really do get at least b to the 2/d points, and so the exponent 2/d is best possible. Let's look at result 3. Let's go back to the previous slide. Result 3 had a form in 4 variables. It was producing a surface in P3, and it had exponent b squared there. But that's going to be best possible because at this point we haven't excluded the trivial points. So here are counting points like these that line a line in the surface. And we said before that those contribute b squared points. So the exponent 2 is best possible for that reason. Whereas in the fourth result, where you get an exponent strictly less than 2 after you exclude the trivial points, well, that exponent can be reduced further by more sophisticated methods. But the result does show that lines defined over Q contained in the surface the points on those will dominate all other points. So there are b squared points contained on any one line, but all the rest contribute at most b to the 52/27. So points on lines dominate. Well, there's one nice corollary of this last result. So let's take a binary form with integer coefficients, homogeneous, irreducible, of degree d at least 3, with a positive leading coefficient. So it might be x cubed plus y cubed or something more complicated. Well, then the values that this assumes, if you put in integer variables x and y, you get something of exact order b to the 2/d distinct values between 1 and b. And the number of these that are taken in more than one way is of order b to the 2/d minus delta for some positive delta. So if you ask how many integers up to b are sums of 2 cubes, the answer is constant times b to the 2/3. And if you ask how many of them are sums of 2 cubes in 2 essentially different ways, well, that's b to something smaller than 2/3. That's actually in stark contrast with what happens with sums of 2 squares, where the degree d is 2. So here I've required d to be at least 3. But if you look at sums of 2 squares, well, the number of integers up to b that are sums of 2 squares is slightly smaller than b to the 1. It's of order b over square root log b. But almost all of those are sums of 2 squares in several different ways. I'm not going to specify exactly what I mean by essentially different ways. Certainly, if a number is a sum of 2 cubes, x cubed plus y cubed, well, it's also y cubed plus x cubed. But if it's x cubed plus 8y cubed, and x happens to be even, well, you can rejig things, swapping x and y in a more complicated way. So how could this possibly be a corollary of the results I've mentioned before? Well, the idea is to look at the equation g of xy equals g of u v. This is saying that we have a number that is represented by g in what appear to be two different ways. And this equation defines a projective surface. So we can apply the previous results about projective surfaces. And we've said that almost all solutions to this equation lie on lines in the surface. So an obvious line would be given by the equations x equals u, y equals v. So that will produce solutions of this equation. So unless there are other lines, almost all solutions of this equation are given by x equals u, y equals v. And that says that almost all the time, if something is represented in two ways, then it's really the same way. In general, you have to understand how it is that lines on the surface correspond to automorphisms of G, and that's what really means that you get essentially the same solution of Gxy equals n if the two solutions are related by an automorphism of G. You can find further details of this in the references I gave. So let's look closer at statement 2, which said that if you have a curve defined by a form in 3 variables, then the count for projective points is of order b to the 2 over d plus epsilon, where d is the degree. Now, I hope you're familiar with the theorem of faultings that says that if you have a projective curve and the genus is at least 2, then there are a finite number of points. So this counting function is bounded. So isn't that a stronger theorem than the statement here? Well, of course, in many ways it is. But what is important here is that while in the context of Faulting's theorem, it is conjectured that the bound here only depends on G, the genus, and hence on the degree, although that's conjectured, it's not presently been proved to depend only on the degree. So it's quite possible that the bound in Faulting's theorem depends in some complicated way on which curve it is you're talking about. So there are estimates for this that depend on the rank of the Jacobian of C and various other bits of information, but those are not independent of the curve. On the other hand, this estimate has an implied constant here that depends on epsilon and on d, but is otherwise completely independent of the curve. And there are various applications where it is crucial to have a bound that is independent of the curve, only depending on the degree. So we'll see that in action next time. So one of the features of the determinant method is that it produces bounds that are independent of the curve. We have the same phenomenon with curves of genus 1, and in particular with elliptic curves. So, as I mentioned before, the counting function for an elliptic curve grows like a constant times log b to the r over 2, where r is the rank. But when you prove this, the constant you get here depends in a bad way on c, the curve. And indeed, although some people conjecture that the rank is bounded, the best bounds we have for the rank at the moment depend on the curve in a way that would make this function conceivably tend to infinity faster than a power of a logarithm. but the theorems that we have proved by the determinant method, they give b to the 2 over d here, but a constant that doesn't depend on the curve. So let me explain how this uniformity issue is handled. Let's look at the case where we have a form in 3 variables of degree d. And I'm going to assume it's a primitive irreducible form. So primitive, remember, means that the coefficients of f don't have a common factor. Then there's an easy theorem that I'll prove in a moment, which says that either the counting function up to b is of size at most d squared, or the height of the form, that's the maximum modulus of any coefficient of this form, is at most this rather large power of b. Well, typically, what the determinant method produces in the first instance is a result that does have a dependence on f, but in a mild form. It will produce something which says you have a bound b to the theta plus epsilon, where theta might be 2 over d, for example, and then a power of this height of f to the power epsilon for an arbitrarily small epsilon, with an implied constant that depends on epsilon. But in the first instance, you do get something that does depend on the form f. But now you look at this lemma, and you see either that NBF is bounded in terms of d anyway, so you get a bound of that type with a 1 there, or the height of f is at most this large power of b, in which case this f to the epsilon is at most this power here of b, but with an epsilon in the exponent. So we have b to the theta plus some multiple of epsilon. So if you just replace epsilon by a suitably small multiple of epsilon, you get b to the theta plus epsilon. This almost seems like black magic. You start off with a bound that includes f to the epsilon, and you end up with a bound that doesn't. It's really rather clever. Well, how do you prove that estimate, that lemma? Let's assume that, let's define n to the d squared to be d squared plus 1 and assume that the counting function is bigger than d squared. So that's ruled out this option. In that case, there are solutions x1 to xn, distinct solutions of fx equals 0. And when I say distinct, I mean projectively distinct. And they'll have height at most b. So we have at least this many essentially distinct solutions. And now we're going to define the number capital M to be d plus 1 times d plus 2 over 2. And this is the number of different degree d monomials in x1, x2, x3. And then we construct a matrix, capital C. It's going to be an n by m matrix, where the ith row, so I runs from 1 up to capital N here, contains the various monomials of degree d in x1, x2, x3. So m is the number of different monomials, so that's the number of columns that you get. Now, let's write bold F to be the vector of coefficients of capital F. So capital F was a form of degree d. It's the sum of various monomials of degree d with various coefficients, and the coefficients make up the vector F. So the fact that the xi are solutions of capital F equals 0 means that the matrix C times the vector F is 0. So you get the various entries of this here are made from multiplying the row of monomials in xi by the vector of coefficients of capital F. So you get the various values of f of xi here. They're all 0. So CF equals 0 does have a non-trivial solution F. And in particular, that means that the rank of C is strictly less than capital F. Now, once you know that the rank of C is less than M, you know how to find solutions of C, G equals 0. You can build a solution by using various subdeterminants of C. So you can find a solution of this for some integer vector G, and because it's built up of subdeterminants of C, it will have size B to the power D times M minus 1. B to the D, that's the size of the individual entries of capital C. M minus 1, because you're building it up out of appropriate subdeterminants of C, typically M minus 1 by M minus 1 determinants. But of course, if CG is equal to 0, that produces a form capital G of degree D, of height at most this, that's the bound that we have here, but with the property that G of xi is 0 for all of these xi's. So knowing in the first place that F has solutions xi, we produce a new polynomial G that also has solutions xi, constructed out of these subdeterminants. And so we know we have control over the size of the coefficients. Now we've constructed things so that F and G have at least d squared plus 1 common zeros. And Bezout's theorem will tell us that F and G have at most d squared common zeros unless they have a common factor. But we took F to be irreducible and primitive, so the only way that these can have a common factor is if G is actually an integer multiple of F. And that gives us our bound. So the height of F will be at most the height of G, which is at most this. So the height of F will be of order b to the, well, when you work it out, it's d squared times d plus 3 over 2. So that concludes the proof of the lemma. You'll see that it involves constructing matrices of monomials, and that is the essence of the determinant method, in fact. We'll see much more of that tomorrow and the next day. So that concludes today's lecture.